Okay, I have air in a piston and a cylinder assembly here. It's initially at 4 bar, 600 Kelvin, volume of 0.43. Okay, it expands isentropically to a pressure of 1.5 bar. So I want to find the final temperature and the work. So I'm going to figure out my states here. So I'll start with 1 and 2. Okay, so initially I'm at P1 equals 4 bar, T1 equals 600 K, V1 equals 0.43 meters cubed. Then it says it expands isentropically to P2 equals 1.5 bar. Okay, so here's what I'm doing here. Okay, to find the work, I need my U value. So ultimately what I'm doing is I'm coming through U. Now for for air, as long as I know the temperature, I can do that. So I can look this guy up right here. Okay. Then, because it's isentropic, okay, we're going to use the relative pressure ratio to figure out what state 2 is. So what do I mean by that? So I have this equation, PR2 over PR1 equals, P2 over P1. And again, we'll look up these PR values in the table. These are good for isentropic processes. And that relative pressure ratio is equivalent to the actual pressure ratio. Okay, so I'm going to look up PR1 and then use it to calculate PR2. Once I have PR2, then I can look up T2 and U2 and finish solving the problem. Okay, so let's go ahead and look up state 1. So I'm at 600 Kelvin. This is for air. So again, I'm in my air table right here. I go to 600, okay, and I look up my U value because again, it's a closed system, and I get 434.78. And then you'll notice right here, when delta S equals 0 for isentropic processes, I can use these relative pressure, relative value. I'll use pressure because pressure is what's given to me. Again, I can only use this when I have isentropic process, delta S equals 0. So I'm going to use this relative pressure of 16.28 to help me figure out what's going on with the next state because I have this isentropic process. So let's jot those two numbers down. Okay, so U1 is 434.78. And then PR1 is 16.28. So this is what I'm going to do now. I'm going to use this equation to find PR2. Again, because this is an isentropic process, I can use these relative pressures, which is the easier way to do things with air. And that means PR2 then is 1.5 bar divided by 4 bar times PR1. Oops. Well, let me do it this way. 16.28. Right? From that, I can calculate PR2 to be 6.105. 6.105. And again, I can do that because this is an isentropic process. Now that I have PR2, I can look that up in my table to find T2 and U2. So again, I'm looking, it's about 6.1. So I scroll down my PR values until I find 6.1, which is going to be right in here, right between 450 and 460. And when I do my interpolation, I actually get 457. And then I can do the same thing with my U value, which is going to be between 322, 329, because again, I'm at 6.1, and I actually get 327 for my U value. Okay, so I use that PR value because it's an isentropic process for air. And I find that T2 is 457 Kelvin, which is the final temperature that I'm looking for, and U2, which is 327.78. So then I can find my work, okay, as simply delta H, or not H because this is a closed system, it's actually just U2 minus U1. When I do that calculation, I get hold on. Yeah, actually this is going to be negative U2 minus U1, and again that's because Probably skipped too much steps here. Q minus W is delta U. So to solve for that, I bring the negative actually to the other side. Right? So it's like this. And that goes away. Bring the negative to that side. Okay. And when I plug those values in, I actually get 107 kilojoules per kilogram on this. Okay. So again, for isentropic processes with air, the easiest way to do it is using these relative pressures. Okay. Because I know this pressure ratio. I know my state here. I can look up PR1. From that relationship, I can find PR2. Once I know PR2, I can go back into that table and find the values I need to solve the problem. Again, these pressure ratios only work when it's isentropic. Okay, so keep that in mind when solving these types of problems.